Third one, so here, gases, right? The next topic here, combined gas law, relating Boyle's, Charles, and Avogadro's law when comparing two sets of conditions, right? The initial and final condition. The combined gas law is P1 V1 divided by N1 T1 equal to P2 V2 divided by N2 T2. So we have here two sets of conditions, right? So in the previous video, we saw that each law has one different equation, right? Avogadro's law, Gay-Lussac's law, Boyle's law, and the Charles law here. So if you learned the combined gas law, you can use this equation here to find all another's equation. For example, Avogadro's law. Avogadro's law is what? Is when the pressure and temperature is constant, right? So here, pressure constant, temperature constant. So you use the combined equation and it cancel out what is constant. In that case, he cancel out P1 with P2 because they are the same. And it cancel out T1 with T2 because they are the same here. Pressure constant and temperature constant. When you cancel out the variables, the parameters that are not changing, right? You have here V1 divided by N1 equal to V2 divided by N2. That is exactly the equation for Avogadro's law, right? In that case here, for Gay-Lussac's law, what is not changed, right here? Gay-Lussac's law, moles and volume, right, are the same here. So for Gay-Lussac's law, moles and volume, right, are constant. If they are constant, they will not be in the equation, right? So let's write this equation here. To combine it law, right? P1 V1 divided by N1 T1 equal to P2 V2 divided by N2 T2, right? Let's cancel out what's constant. In Gay-Lussac's law, mole is constant. Okay, let's cancel moles with moles. And volume is also constant. Let's cancel volume 1 with volume 2. So now let's write what we did not cancel out here. So P1 T1 equal to P2 T2. That is exactly the Gay-Lussac's law, right? That's in here. So the same thing for another ones. We do not need to memorize each individual equation. So, but if you memorize this equation here, you can find all another ones. Like, depends on the question is given. But for example here, the gas pressure, this question here, the gas pressure in aerosol is 1.5 atm at 25 degrees Celsius. So assume that the gas volume and amount of the gas are constant, what is the pressure when the can is heated to 450 degrees Celsius, right? Okay, so let's write the combined equation first here. V1, V1, N1, T1, right? Equal to P2, P2, divided by N2, T2, right? Now let's cancel what is constant. Gas volume, let's cancel V1, V2. And amount of gas is about mole numbers, right? So what you have here then? What did not cancel out was P1, T1, and P2, T2, right? Now let's plug the numbers here to find what's the final pressure. But first thing, the temperature in Celsius, right? Need to convert to Kelvin. How go from Celsius to Kelvin? So the T1, right? 25 plus 273, right? So T1 will be what? Here, be 298 Kelvin, right? So you can see here, 298 Kelvin. The same thing for, so here was T1, now T2 in Kelvin, it will be what? 25, sorry, 450, right? Plus 273. What are gonna be your T2 now here? So go 450 plus 273 will be what? Here, like 723 Kelvin, right? Now let's plug here. P1 was given, right? So P1 is 1.5 divided by T1. T1 is 298 Kelvin. And then P2 is what we do not know. Let's write it here, P2. Then the final temperature here is 723 Kelvin, right? So here we are going to solve for to find P2 here, and then you can solve the problem. So your final, you know that your pressure will be in ATM here. Okay. All right, just so like using the combined gas equation, you can find all another equations here. Just need to pay attention what the question is saying. The question is saying, for example, the volume and amount of gas are constant, or if it's like, and if the question does not say, for example, here, if the question did not say about volume, you will assume that the volume would be constant. So the question will have two ways to talk about what's constant. One is really saying clearly shown that it's constant, or just the question does not say anything about what is constant, right? Okay. So ideal gas law relates the pressure, volume, moles, and the temperature of a gas, and is used to approximate the behavior of real gases. So you saw that combined gas law is what? Q1, V1, right? And 1 divided by Q1 equal to P2, V2 divided by N2, T2. This is the combined gas law equations. And the variation of ideal gas law at like pressure, volume, mole numbers, and temperature here is equal to a constant. So this ideal gas law equation is PV equal nRT. Pressure, ATM, volume, liters, N in moles, R is the universal gas constant, and T will be in Kelvin. So the R, you have different values for R. It depends what you need, right? For example, if you have a question related to pressure, moles, volume, you'll be using this R here. So I could be also going to be using this R in the questions. R is equal to 0.08206 liters at atm per mole Kelvin. Okay, so you have this R, this value. If you need to use it in energy, you'll be using different R. But for the questions about pressure, volume, and temperature, we'll be using this R here, the first one. Okay. The next topic here is manipulation of ideal gas law equation to determine the density of a gas. So the density, what's the formula for density? Density is mass divided by volume, right? Okay. And what's the ideal gas law equation? Here. So PV equal nRT. And what's the formula for moles? Moles is equal mass, right? Divided by molar mass. Okay. So let's try to manipulate these equations here to find the density of a gas. So let's start with this one, right? PV equal nRT. And so in density, you need the mass and the volume, right? In the equation, you do not have a mass, but you have mole numbers. So let's replace this mass over molar mass here. So PV equal to mass over molar mass, right? Times RT, right? So you use this portion here, right? To replace this one. And what's density? Density is mass over volume, right? So we need to manipulate this portion here. Then we're gonna have pressure times molar mass equal to mass, right? Divided by volume times RT. And what's mass divided by volume? Density, right? Now let's rearrange it here. So we know that pressure molar mass, right, is equal to density times RT. So in order to calculate the density of a gas, we know what we're going to, so for D, right, for density will be what? Pressure times molar mass divided by RT. So to calculate the density of a gas, right, we're going to use this formula here. Like for the question, give us pressure, molar mass, R, in temperature. We are going to solve using this equation. Like, don't need to memorize this equation here. If you memorize this one you should already know, right? And then you can manipulate to arrive in this equation here. Right? Calculate the density of a gas. Now, how to calculate the molar mass of a gas? The same similar way, right? So you have moles number, right? N is mass divided by molar mass, right? And what's the ideal gas law equation? PV equal nRT. So pressure, volume. Let's replace this N here by mass or molar mass, right? Because you needed to have the molar mass in the formula here, right? Let's take the mass here, divide by molar mass, times RT. Now rearrange the formula, right? To solve for molar mass, the equation will be molar mass is equal to mass, right? Times RT divided by pressure times volume, right? So here, manipulate the ideal gas law equation to find the density formula for gas, to using gases, and the molar mass. So here you have some steps to solving gas law problem. So using the units of the values provided in the question to identify which properties have been provided in the question. So pressure usually be given ATM, torr, and volume in liters, cubic centimeters, temperature in Celsius or Kelvin, and amount of gas will be usually in moles or grams. So once you know what properties you have, you can know which gas law equation you are going to use, right? So we need to read the equation, figure out, okay, what is the same? What is changing, right? The parameters that they are constant will be canceling out, like here, right? And we're going to use in the equation only the parameters that they are changing. So now is about stoichiometry and the gases, right? So stoichiometry, you need the first thing, make sure the equation is balanced, right? Right, okay, so using stoichiometry and gases, we're going to take the ideal gas law equation first. So use the data for mole numbers and the ideal gas law equation, PV equal nRT. Use the relation moles of all the reactant products, and then answer the question, right? So here. So we have here this question talking about the automobile are bags that are inflated by nitrogen gas generated by the rapid decomposition of sodium azide here. So we have the equation balanced here, right? If an airbag has a volume of 36 liters and is to be filled with nitrogen gas in 1.15 atm in 25 degrees Celsius, how many grams, right, of sodium azide here must be decomposed? Okay, so let's use a ideal gas law equation to find the mole numbers of nitrogen, right? So what you know here, ideal gas law equation is PV equal nRT, right? So talking about stoichiometry, you need to find the moles, right? So let's solve here for moles. Moles is pressure times volume, right? Divided by R and T. Okay, so now let's get the numbers here. Pressure 1.15 atm, right? Volume 36 liters divided by R. R is the universal gas constant, right? That you saw here. 0.08206, 0.08206 liters atm per mole Kelvin, right? Times the temperature in Kelvin. So the temperature here, you have 26, right? So 26 plus 273 will be 299 Kelvin, right? So let's calculate here how many moles of hydrogen we have right here. Okay. Right, divided by times 299. So you have here 1.68687, right, moles of nitrogen. So let's use it here. So 1.687 moles of nitrogen. So what's the relation between nitrogen and NaN3? Okay, right. So how many moles of nitrogen you have here? Right? You have 3 moles of Na2. And how many moles of NaN3 you have here? 2 moles, right? Right now, let's find how many moles of NaN3 you have here, right? Times 2 divided by 3. So 1.687 times 2 divided by 3. So you have 1.4 moles of NaN3. So right now, I'm not too worried about significant figures yet because the question, we don't have the final answer yet, right? Okay, so now how go from moles to grams? From moles, right, to grams, we're going to multiply by the molar mass. Okay, so let's go here. It's 124 moles of NaN3, right? So you know that it's 1 mole of NaN3. You have how many, what's the molar mass for sodium? So right, sodium here, around 223. It's nitrogen, the molar mass is 14. So we have 3 nitrogens, right? So 14 times 3 plus 23. The molar mass of NaN3 is 65 grams, right? So let's multiply 65 times 1.124. You have here 73 grams, 73.1 grams of NaN3. So that means we need to get the 73.1 grams of NaN3 must be decomposed to form to have this amount of nitrogen gas here. All right, so right. Okay, so part 3 here, theory. Why do you observe these laws behaviors? Right, so the gas consists of large numbers of molecules. They are in continuous random motion. So the continuous random motion, and the pressure inside the container comes from collisions of gas molecules with the container walls. And the every kinetic energy of the molecules is proportional to the absolute temperature. That means increase the temperature will increase the kinetic energy, right? Now, movements of a gas molecule. So you know that the temperature is related to the every kinetic. And the individual molecules can have different speeds. Right, so this first one here is the speed exhibited by the larger number of molecules. This one here is the average mean speed of all molecules. And this one here the speed of molecules whose kinetic energy is equal to the average, the kinetic energy of all molecules here. So we have here MP is the most probable, and this what AV is the average speed of molecules. RMS, the root mean square speed, is the one associated with the average kinetic energy. That's what we're going to have here. Calculate this. Root mean square speed will be square root of 3 times R times T divided by molar mass, right, of the gas here. And this R here will be a different R, will be 8.314 joules per mole Kelvin. And what we need to know also is that if a gas has a low mass, its speed will be greater than for a heavy molecule. So lighter the gas, faster it will be, right? Right. So then you have here Green's law equation, Green's law, effusion and diffusion. Effusion is the escape, right? So you have a hole here. The escape of the gas molecules through a tiny, tiny hole into evacuated space here, right? And diffusion is the spread of one substance throughout the space or a second one. Diffusion here, right? Spread out. One substance through a second substance here, through the space or a second one. And Green's law relates the molar mass of the two gases to the rate of speed of travel. In the lighter gas, always has faster rate of speed. So here, the equation, Green's law equation is the rate of speed of gas 1 divided by the second gas, right, is equal to the square root of molar mass of gas 2 divided by gas 1. Right? And now here, deviations from ideal behavior real gases. So you saw in ideal gas law, right, that for the gas behave ideally is to be in high temperature, right, and low pressure for ideal gas. But in other conditions, the gases will not behave ideally, so it's going to be real gases. So in the real world, the behavior of the gases confirm the ideal gases equation only at relatively high temperature and low pressure. So even the same gas will show widely different behavior under high pressure and different temperatures. The assumption made in the kinetic molecular model, negligible volume of the gas molecules themselves, so no attractive force between gas molecules. So in ideal gas conditions, we assume that they are behaving ideally and no attractive force between gas molecules. But this condition here will break it down at high pressure and low temperature here. So in ideal gases, right, the gases, they don't have attraction between, like, no, there is no attractive forces, but in real gas, yeah, they will have attractive forces here at high pressure and low temperature. Right, so the ideal gas equation, right, is the equation here, V equal nRT, can be adjusted to take these deviations from ideal behavior into account. So one equation corrected for real gases is known as van der Waals equation, is here. Van der Waals equation is correct in the pressure portion, right? Here. Pressure and volume, right? Pressure times volume equal to nRT. Now we're seeing here that for ideal gases, we have a different A, so we have A for each gas. So the and B for each gas here. So this equation here for real gases is van der Waals equation. So one equation correct for real gases is now a van der Waals equation. In the pressure adjustment here, we have adjustment here, is due to the fact that molecules attract and repel each other. In the volume adjustment here, is due to the fact that molecules occupy some space on their own. Like you see here, each gas has different value for A and B, right? Okay, so is the end of chapter 10.